Dr. Mohammed, do you see the recording from your side?
Yes, I see.
Okay, so let's begin. So, Luis, can you mute your microphone, please? Luis Muller. Okay. Dear all, I would like to welcome you all to our webinar number 1 in 2026 regarding to introduction to pulse neutron logging and application within interactive petrophysical software. Were presented by Mr. Rose from Geoactive company. My name is Mazen Hilali. Currently, I'm a senior petrophysicist with the local in West Gunna project, Iraq, Basra. First of all, I would like to thank Mr. Rose for his third webinar with SPWLA Iraq, and special
You're
thanks.
welcome.
Thank you so much. And special thanks for Geoactive for their yearly presence, fourth year, a row with SPWLA event. I will leave the floor to Dr. Mohammed Jawad, VP of Technology with SPWLA Iraq. Dr. Mohammed, floor is yours.
Thank you, Mr. Mazen. And distinguished guests, good day. It's my pleasure to welcome you to today's session organized by SPWLA Iraq chapter. My name is Mohammed Jawad Zain Al Abidin, and I serve as the VP of Technology for SPWLA Iraq. I hold a PhD in Petroleum Engineering and am a senior faculty member in the Department of Petroleum Engineering at the University of Kirkuk. We are honored to host the first webinar of the 2026 SPWLA Iraq webinar series. Today's presentation is entitled Introduction to Pulse Neutron Logging and Applications within Interactive Petrophysics Software. This session will be delivered by our distinguished speaker, Mr. Rose Brackenridge from Geoactive Limited. Mr. Rose, welcome and thank you for joining us.
Thank you. Hello, everyone.
Dear attendees, we kindly ask you to note the following important points. Please keep your camera and microphone turned off throughout the webinar. Kindly be informed that the session will be recorded. If you have any questions, please type them in the chat box. The speaker will address them during the question and answer session at the end of the presentation. Additionally, a link to join us or to join the SPWLA Iraq community on LinkedIn will be shared in the chat box during the session. Thank you for your attention and participation. Mr. Mazen, the floor is yours.
Thank you, Dr. Mohammed. Just I will make very short presentation. Okay, let me see. Sure. You can't see my screen. That have presentation?
Yes, Mr. Mazen.
Okay. Okay, so thank you again for attending SPWLA Iraq monthly meeting. This webinar is about introduction to pulse neutron. Will be presented by Mr. Rose Brackenridge. We expect to hold 8 to 10 webinars. We're still in the planning stage. Next month, most probably will be BP. Next month will Kappa, Schlumberger, and afterward. And I'd like to thank all of our sponsors for this one. As per yearly tradition, we'll give like a special award to anybody who have attended 6 of our webinar, and will be awarded in December. I will correct this one, December 2026. Last year, 2 persons have been get this certificate. I'd like to thank them. And anybody is welcome to join Iraq chapter officially, or he can just follow with our events, like we provide them free of charge. Question and answer will be kept at the end of lectures. Kindly keep your camera and mic muted. Thank you all. Mr. Rose, the floor is yours. And if you like, you can introduce yourself in more detail. Thank you so much.
Okay, thank you very much, and welcome everyone. Looks like we've got a good attendance. Let me just share my screen. Okay, so yes, today's presentation is, usually it would just be, my session would be talking about IP software and how we do pulse neutron in our software, but because I'm the first person as part of this series, I thought I would, talk a bit about more of a general introduction to pulse neutron logging, and then I'll talk about how we handle data in our software. Yeah, I've been in the industry for, I think that's out of date now. I think it's probably about more like 28 years. Firstly with a service company where I did various roles with log analysis, geoscience management, business development. During that time, the theme was always around cased hole. Whichever job it was I was doing, it was usually around the cased hole business. So the casing inspection, production logging, pulse neutron, cement evaluation. But in the past, again, sorry, it should be about 13 years, I've been with Geoactive, who are providers of geoscience software. And I've been building up a suite of modules within the IP platform, which is Interactive Petrophysics. Just a little bit about IP. So what is IP software that we work for? So it's a powerful subsurface data interpretation package. Its main focus is on petrophysics. So it's best known for its kind of open hole interpretation, where it would calculate rock properties and fluids like porosity, clay volume, saturation, and a lot more. It's been around for about 25 years in the market, so it's very well established, and it's one of the global leaders in its field. It is mainly petrophysics at its core, but over the years we have branched out into other specialist areas, including cased hole. So our product can be used by quite a wide range of the subsurface disciplines. And because of that, it's not something that's just used at the exploration stage. It can be used right throughout the whole development, production, and abandonment of an asset. So I say we've got different specialist suites within the software. This is IP here. You can see these different menus down the side. Here we have cased hole. We have well diagrams, casing inspection, cement evaluation, production logging, but you also have these modules here, pulse neutron modules for Sigma CO, and we'll see if we can do some other types of workflows as well. So this is what I'm going to be talking about today. So as a brief introduction to pulse neutron logging, then I'll talk a bit about these different types of analysis. So if we talk about pulse neutron logging, that we're talking about a type of tool, but that tool can be logged in different logging modes. And each of those logging modes requires a slightly different way of interpreting data as well. So we'll talk about how it differs between the logging modes. So pulse neutron, why do we need pulse neutron tools? Well, we're usually using them to determine what the fluid saturations are in the reservoir. Now, this is usually in a cased hole environment. We did just speak before the introduction there about how there is applications for some of these tools now in open hole as well, but mainly it's a cased hole service. So most of what I talk about, in fact, all of what I talk about today will be from a cased hole perspective, but we might hear more about other applications in open hole in later sessions. So when we're in a cased hole environment, previously, if we had open hole, if we want to work out what fluids are in the reservoir, we could take fluid samples, or we could use resistivity tools or density neutron to try and work out the porosity and the fluid saturations. Those tools are no longer suitable when you have casing and cement in between the tool and the reservoir. So that's why we use pulsed neutron tools if we want to see, find out information about the reservoir behind casing and cement. So these tools, as the name suggests, are pulsing neutrons, fast neutrons, into the reservoir. Now these neutrons can travel through casing and cement. They move into the reservoir and they'll bounce around everything in the reservoir. Now, as the neutrons interact with the environment, they will produce gamma rays. So if there's high energy collisions, we call these inelastic collisions. That means that the neutron continues its journey, but there's a neutron is being emitted. That will get picked up on our detectors. And eventually a neutron will start losing energy with every collision, and it will eventually be absorbed or disappeared. We call that when it's captured. Now, when it's captured, it will also emit a gamma ray. So although our source is a pulsed neutron source, our detectors are actually gamma ray detectors. So we're measuring the gamma rays that have been created due to the interactions of the neutrons. So by looking at how many gamma rays we receive on the various detectors, and also the energy of those gamma rays, we can tell things about the reservoir that these neutrons have interacted with. So what's the tool actually seeing? Well, if we look at this against, so this is time, this is microseconds along the bottom here, and this is counts. So as I said, the tool is going to burst on, fire the neutrons into formation, then it's got to switch off again, and it's got to stop for a period of time, and then it'll come back on again. So this is representing one burst cycle, if you like. So the first 50 microseconds here, the tool has been burst on, then it's switched off, and then we just record the gamma rays over a period of time after that. So what we see is very high counts on this is gamma ray counts when the source is on. Obviously, there's got to be lots of large volume of neutrons interacting with the formation, lots of inelastic collisions, and that's what we're seeing here. And then as the source is switched off, still be quite a lot, but that will start reducing quite drastically. And then eventually it will go back down to what our natural background gamma ray reading is. So this is almost like if the source wasn't fired at all, it would go back down to this. So we record from the burst how it decays right down to when we just see background again. And then we repeat the process. So this has all happened in a second. The tool will be firing every second. And notice we're recording multiple detectors. So the short space detector will see the most counts. Obviously, the extra long space detector would see the least amount of counts. So what can we tell from this spectrum? Well, if we look at this area here, which is used for what we call sigma analysis. So when we talk about sigma, we're talking about a window on this that's measuring the decay here. It's actually after the first phase is going to be a lot of interactions in the borehole. And then once we get into this section, this is more interactions with the formation. So this is the area we're interested in. Now, the speed of how this decays, so that the gradient of that line can tell us about the type of fluid that's absorbed the neutrons. So if we have a very steep gradient, that tells us that there could be a lot of high salinity water present that has absorbed the neutrons quicker. Then if it was a sort of lazier, sort of slower decay, that could tell us that there's hydrocarbon in the formation. So there's not as much saline water, because high salinity water is very good at absorbing neutrons. So we actually, this is happening real time in the field, this spectrum, and we're actually calculating a curve. So we actually create a curve called sigma that represents this rate of decay, if you like. So that's usually the first, would be our first choice in how we use the pulse neutron tool. But if we don't have high salinity water, we may need to look at other parts of the spectrum. And for what we call carbon oxygen analysis, we would look at this section here, so that the high energy inelastic bursts. So we're only looking at when the source is on. Now we can actually measure the energy of those gamma rays as well, and we'll see a little bit more about that. And that can tell us a bit about the water or hydrocarbon content of the formation as well. And then we can also do another thing we can do is we can actually look at the in the same area here where the burst is on, but rather than look at the energy, we can look at the ratio of counts between the various detectors, and that data can be used for determining between gas and liquid. So there's kind of three areas of this spectrum that we might want to use to do our analysis. Now, at Geoactive, we're completely vendor neutral. We're not affiliated with any particular service company. We try and use everybody's tool. So I'm not here to say if any tools are better than others. I am just want to give you a list of, there will be others out there, but this is a list of some of the common tools that are on the market. Obviously, different tools can do different logging modes. And most of them are wireline tools, surface readout. There are slickline tools out there that do sort of more just sort of basic sigma recording. But most of the tools do require surface readout, because for a lot of these logging modes, there's quite a bit of interaction between the engineer and the tool required during the setup when it's actually in the downhole. So we're usually dealing with surface readout tools, wireline tools. So for over the probably the past 20 years or so, the market was kind of dominated, but you have the big four service companies, all with their version of the pulse neutron tool. Schlumberger with RST, You have Baker Hughes with the RPM, Halliburton have their RMT, and then Weatherford have the Raptor tool. So all of these will do sigma and carbon oxygen. And then some of the companies started providing a new gas mode service as well. And then some of these can also be used for production logging purposes as well. So when we're not actually just trying to look into the reservoir fluid saturations, but actually trying to see flow behind pipe and things like that. So there's some other ways of using these tools as well. But we're really talking about this kind of reservoir characterization here. And then more recently, Schlumberger brought out the Pulsar or the PNX, which also provides like a full spectral analysis as well. I believe there are some of the other service companies are also bringing out tools similar to this as well. Maybe we'll hear about some of those in later sessions. But also wanted to mention about these tools. So this is outside of the big four service companies who would manufacture their own tools. So used to be really just the big four that would do it, but now we see some companies, some tool manufacturers that have been able to build tools that can also do sigma, carbon oxygen, sort of gas analysis. And these are tools that can be bought off the shelf. So that means that there's lots of other service companies involved in these services now. So smaller to sort of medium-sized service companies can now use these type of tools as well. Okay, so as I say, I hope I'm not upsetting anyone with this. It might not be 100% accurate, but it's just to give you an indication of the type of tools and the companies involved. A little bit about job planning. This is very important for pulse neutron. As a data analyst, sometimes with certain types of data, you know, it doesn't really matter if you were involved in the planning of the job. You get some data handed to you and you can do a reasonable interpretation of it. With pulse neutron, I would say it's one of the most important data types that the analyst should really be involved in the planning of the job. Because based on things like lithology, porosity, fluid parameters, all these things can decide which logging mode we should be logging in, how many passes we might need to make, and where those passes should be. You know, which zones we should be logging. For example, it's very good for data analysis if you log over a clay section and maybe a zone that's already wet. Now, that might not be obvious to someone that's a logging engineer that's planning the job. They might think, well, they're just going to be interested in the zones that we think there's hydrocarbon in, but taking some other logging some other areas can be very useful for calibration purposes. So you don't want to end up with a data set on your desk that you can't really work with. So if at all possible, if you're a data analyst that's going to be interpreting these tools, please try and get involved at the job planning stage. So this is a bit more specific to IP, that we have these different analysis types, different modules to do those. Our CO module can actually do more than CO. It can do the gas analysis as well. But what do they actually output? So The sigma standalone and the time lapse would, well, standalone would give us a water saturation, formation water saturation. Our time lapse sigma would give us a change in water saturation, a change over time. Carbon oxygen would give us another independent way of measuring water saturation. And then our gas liquid analysis would calculate a gas saturation. So with sigma and CO, although what we really want to know is probably where the oil is, hydrocarbons are, it's actually water saturation that we are calculating, and from that we can infer what the hydrocarbon saturations would be. But that's the outputs of the modules. So sigma analysis. As I say, we're looking at this part of the spectrum of data. But if you imagine this is happening, this whole spectrum is happening multiple times for every log sample that we take. So for every, this is just one point in time. So for every depth or every cycle of the tool pulsing, we get a sigma value. And that, so we end up with a sigma curve versus depth. And that usually would be scaled something like between 0 and 50 would be a reasonable scale to have that. So what can we do with this curve? What does it actually, well, we know what it kind of represents, but well, first of all, what is that sigma curve responding to? Well, the answer is it's responding to everything that's in there, not just the water saturation or the oil saturation. It's responding to everything that's in there. Now, everything, either from the rock, from the clay or the shale to the fluids, everything has a sigma value. And by that, I mean, if you had a tank of only fresh water and you logged that tank, it would probably have a sigma value of about 22. If you logged a block of pure sandstone, it would have a sigma value of something probably between 4 and 8. If it was shale or clay, it would have a much higher sigma value. And notice high salinity water as well has a very high sigma value. So these are the values that you'd get if you logged just these things alone. That's all the tool was seeing. But of course, we're not seeing just one thing. We're seeing everything mixed together. So the sigma curve is really a representation of what the sigma of the matrix is times how much of that matrix we have. Like sandstone, for example, how much sandstone do we have and what's the sigma value of that? Plus the sigma value of the shale times how much shale we have. The sigma value of the water times how much water we have, and then the sigma value of the hydrocarbon times how much hydrocarbon there is. So it's a total that where the log is actually seeing. But we could actually represent that in a different way. So this would be it as an equation, pretty much the same thing. There's our sigma log value, and it's representing all these things that we just spoke about: sigma matrix, shale volume, sigma water, sigma hydrocarbon. And in here we have water saturation. That's part of because we want to know how much water there is, times the sigma of the water would give us part of the sigma response. But this is what we want to actually know, isn't it? This is what we're trying to find out. We actually know, we've got a good idea of most of these other things, either from our fluid properties that we know about or our open hole data. We actually know most of these things before we even log with our pulse neutron. It's this that we don't know. So if we rearrange that equation to solve for SW, the equation would look something like this. We sometimes call this the material balance equation. So what our software is doing then is it's allowing the user to input all values and curves for all these things so that we can work out SW. So the workflow, this would, not necessarily using any software, you'd first bring in the pulse neutron data, prepare it. You might want to depth shift it. If there's multiple passes, you might want to do some averaging of passes. And then we want to gather open hole data. We're going to need the porosity, clay volume. We want to have the open hole gamma ray as well. We would like to have the open hole water saturation so we can compare the old water saturation with the new water saturation. We then need to work out what are the values, the sigma values for the various fluids that are in the formation. Then we actually, when we run the module, we actually create these synthetic curves. Now, synthetic curves, we'll talk a bit more about in a minute, but it's simulating what the sigma may look like depending on what kind of fluid are in the formation. And then we would do some fine tuning. We could adjust, so some of the sigma values that we've started off with might need some slight adjustment. And we can also correct for clay presence as well. And that would give us our final water saturation. So we can compare what the open hole water saturation was like with the new water saturation. So as I say, in IP, we have a sigma analysis module. I'll maybe just switch over to the software for a moment. So I say in here, cased hole, we're looking at the sigma SW analysis module. Now, before I even go into that module, I've got this conversion tool that I can put in what the reservoir pressure and temperature is in the reservoir. I can put in properties of the water like salinity, oil gas oil ratio, the relative SG of the gas, and from that we can get sigma values for all the fluids. That would be the first thing we do, is get these sigma values. Then we can open up the module, bring in sigma, porosity, clay volume. This is quite a simple sandstone environment, but if you did have a more complex environment, you could bring in various mineral volumes into here. And then ultimately we're going to try and calculate our SW here, and there's a few other curves that will be created in the calculation of that. Our parameters, let's say we just calculated what we think our water sigma value is going to be. And this is gas, so this is what the hydrocarbon sigma is going to be. We don't yet know, so unlike with the fluid properties that we can calculate sigma, every clay and shale or whatever is going to be different. So we don't know what the clay, the sigma value of the clay is at this point. We're going to require the data to work that out in a moment. And the sigma of the matrix, as I say, this could be I'd say this would have been probably a lower value to begin with, and I'll show you how we can interactively fine-tune that number as well. But at that point, we can run the module, we can make a plot, and what that does is, as I was saying, we've got these call them synthetic curves, if you like. So this red line, hopefully you can see that properly. This red line is based on that material balance equation that we looked at, is saying this is what my sigma should read if I was in 100% gas. Whereas the blue line here is saying this is what my sigma should read if I was 100% water. So our recorded sigma, which is the green one, should really sit in that range. It should be sitting somewhere in between these two lines. And you can see it is, but it's kind of stepping out in some areas. So that's when we might need to do some fine tuning. But you can see at this stage, we've already got a result, a result, not necessarily the exact correct result, but it's already showing that these, with the dark blue is the open hole bulk volume of water, and this kind of aqua color is showing the where the water saturation is now, so the displaced hydrocarbon. But to do a bit of fine tuning on this, we can we could launch this cross plot, which is showing us our porosity versus sigma. And you can look at that with the data on top of it. Now, each of these points represent the sigma values of some. So this one is the sigma value of the hydrocarbon, sigma value of the water, sigma value of the matrix. Obviously, the data is all quite low here because this is the porosity that we're in, around about 20% porosity. So these sigma values are sitting where they would be 100% hydrocarbon and 100% water. So we can adjust these. So if I think that this is a clay response here, by the way, so we are expecting most of the data to sit within this window. So this is showing, so if it was 100% hydrocarbon, the data should be sitting on this line. If it's 100% water, it would be sitting on this line or somewhere in between. As I say, this would be the clay that's causing this to step out of the model. But we can interactively change some of these values. And as you see it, as I'm doing that, it will update these numbers and it will also update the interpretation. So you can see how a small change in one of the sigma values, the impact that it has on the end result. So we might be saying that, okay, well, it looks like we've got almost too high water saturation in this zone. We don't have almost any residual left. So maybe this should be a bit higher. And that might be a bit more sensible with some residual oil, gas in there. So there's that ability to, you can start off with what you think the sigma values are, and you can do some fine tuning. The other big thing that we need to address is the presence of the clay. You can see where we do have some clay at the top. We've stepped out of the model, which isn't good. We want the curve to be in the model. So I can launch this clay versus sigma. And you can start to see a pattern here, a trend. As the clay gets higher, the sigma value gets higher. Because remember, clay has a very big sigma value, so a lot of that data is being affected by the presence of sigma. So we need to kind of compensate for that. So now the reason there's so many low values here, we're not seeing much values in this area, is because we never logged a 100% shale zone. If we had, I would have been seeing data coming right up here, and I would have been much easier to work out my 100% clay. But so without that, we just need to extrapolate. So something like this might be our sigma clay value. So that's about 63. And now when I did that, you can see the interpretation as the model has now changed because it's corrected for the presence of clay. My data is now sitting in the envelope, which I'm happier about. And now we can see that we've got some more sort of sensible results, that we've just got residual hydrocarbon there, and then we've got a definite contact here, but it looks like the hydrocarbon is the same as it was at open hole. Now, this was done as a sort of standalone interpretation. So in other words, we had one pulse neutron log. But what if you were monitoring this over time? You went back again in a couple of years to log again. We can do a slightly different type of analysis, which is the sigma time lapse. And it's a lot simpler because things like clay volume, none of that's going to have changed in between over time. So if we get a change of sigma, we know the porosity is unlikely to have changed much. We know the clay volume, the lithology is not going to have changed. Any change in sigma, we can say is going to be likely down to changes in fluid. So the parameters involved in this are not so much. Sorry, I just need to get this out of the way a little bit. So this was our previous sigma analysis, and if we look at the time lapse from 2 years onwards, so this was, the first one was actually logged in 2012, the second one was logged in 2014. So what this module does is effectively just overlays the sigmas, compares them, looks like there's no change throughout here, but where we see this yellow spreading, that means sigma has changed. So we can actually put that down to a change in fluid saturation. So we can now see this zone near the top, which was hydrocarbon bearing in 2012, is now almost completely water filled up to about this depth in 2014. So just another way of doing it if you are working with multiple pulse neutron logs over time. The interpretation is actually a bit more simple than when you're doing just a standalone one. So that was all possible because where's my conversion again? When we did our conversions, we had a very high water salinity, 210, that gave us a sigma value of 102. That's a huge difference between the sigma of gas, which was 6. That's why we had that big spread between gas and water, and we could get a nice interpretation from that. But what if our, what if we had very low salinity water? You might have that might be a sigma value of like 38 if we had only had like 50 kppm. What if we had even lower, down towards like seawater or something? Then we've got a sigma value of 32. You could maybe do something when you have gap between gas and water, but it's going to be much more difficult than if you had oil rather than gas. The sigma value between oil and water just becomes too close. You just can't tell the difference, not accurately anyway. So when we have, if at the job planning stage, we have a much lower sigma for water, and we're going to have a problem distinguishing between these, we would have to think about changing from sigma to carbon oxygen. So carbon oxygen. Now remember, we were looking at the spectrum, the time spectrum from the Sigma tool, which actually records, sorry, not the Sigma tool, from the Sigma logging mode, which actually records the spectrum source on, source off. We look at the decay, and we keep recording right down until there's the background gamma ray. Now, in CO logging mode, we don't really need to keep recording for that long after source burst, because the data we're using is in this source burst. So what we tend to do is source burst on, wait a small amount of time, and then back on again, because we're really wanting to get as many of these source bursts as possible. Now, what we can do as well, or what happens real time with the tool, is it will not only be counting the gamma rays, but it'll be looking at the energy of those gamma rays and building an energy spectrum. So here we have counts, but this is energy that's along here. So anything that a neutron interacts with these inelastic collisions, the energy of the gamma ray can tell us what it was that the collision, the neutron had collided with. So if it was carbon, there would be it would have an energy of about 3.4 or something. Oxygen is just above 5. So as we log, as we do these bursts multiple times, we start seeing peaks developing on here between carbon and oxygen. Now the ratio, we can create a curve that is a ratio between this peak and that peak, or this window. So different service companies do it slightly differently. Some of them take a whole kind of window, add up the counts. Others look at the peak, so actually get the yield peak and look at the ratio of those. But either way, we end up with CO curves. And we will have near detector curves and far detector curves. Now, CO data is quite statistical. It's not as accurate as Sigma. So you can see here, if we do multiple passes, they're not all overlaying perfectly like we do with their Sigma. So we need to do multiple passes, usually with CO, probably between 3 and 5 passes. Traditionally, I know some of the newer tools have got ways of cutting down the amounts of passes that they need to do. Maybe someday we'll talk about that later in the series. But generally, with CO, you're dealing with multiple passes. So there's a lot of data management. You kind of want to get all these on depth. You might want to do some filtering. You then want to do some averaging between the near and far. And then in some cases, you might also want to then take a weighted average between near and far. Now, this is where we're getting into slight differences between different service companies. So a Schlumberger approach should actually be to cross-plot near and far. So keep the near and far CO curves and use them both in the interpretation. And this is, we would get this to interpret, there's this quadrangle, if you like, and this is representing each corner is like a different fluid in the borehole and a different hold-up. So this corner here would be data that represents a hold-up, an oil hold-up of 100%. So 100, so basically an oil-filled borehole, but 0% water saturation in the formation. This would be still oil in the borehole, but 100% water in the formation. And then this is with the borehole filled with what would probably be water, because it's 0 oil. This would be 100% water in the formation, or 0% water in the formation. So it's looking at potentially two different borehole fluids at once. What Baker Hughes do, and a lot of the other service companies do something similar as well, that they would assume that whatever the borehole fluid is, so they would have a fan chart for a particular borehole environment. So this would be for either a water-filled borehole or a diol-filled borehole. So it's one chart that's representing one borehole environment, if you like. And then we plot a compensated CO ratio, which is either averaged or weighted against porosity. And based on where the data lands, a bit like the sigma interpretation we saw before, we've got a water line if it was 100% water, and an oil line if it's 100% oil or hydrocarbon bearing. So you can imagine the data sitting in here, and where it sits would determine the water saturation, just like in the Schlumberger one here. The data here would depend how far up that line it is, would depend the formation water saturation. So the workflow for carbon auction, certainly for, well, in IP software as well, you take the petrophysical properties and data to understand the environment we're logging in terms of porosity, clay volume, fluid parameters. Then we need to, it's very important to understand the borehole environment, more so than sigma, because remember, with sigma, the part of the spectrum that we were looking at was after the borehole interactions. So in effect, that sigma was already corrected for borehole presence. But with carbon auction, because we're looking at the inelastic counts, which are quite the early counts, it's heavily influenced by borehole interactions. So we really need to understand what borehole size we're in, what casing we're in, what fluids are there, because if anything changes, the tool response is going to change. We're going to get a step change. So based on the environment, the petrophysical environment and the logging environment, the borehole, we need a response model. So every carbon auction tool on the market will respond slightly differently to the others. And that same tool will respond completely different in different environments as well. So we need a model that's specific to this tool in this environment. Then we bring the data and the model together and we make these synthetic lines, a bit like we did with sigma. This time it's oil and water. And then we do some fine tuning again, such as clay corrections, normalizing the model, and ultimately we get water saturation, cased hole water saturation. So just want to quickly show that in action as well. So here, if we go to a carbon auction well, carbon auction analysis, so we're bringing in our CO and some of our open hole data as well. We can bring in sigma, fluid density, caliper if we have them for reference. Ultimately, we're going to calculate a COSW, and there's various other curves that will get calculated in the process of that. But here is where we put in our well information. We can bring it in from a well diagram, or we can put it in manually. Makes sense to make a diagram first and then bring it in. So this is just telling us what the borehole size is and casing is, and what, based on what our logged interval is. If we hit apply here, or sorry, if we hit create here, it can create zones depending on every time we have a change in casing or borehole size. So just a way of knowing how many zones we're maybe going to need. Hopefully ideally you only have one zone, because every time you have a borehole change, you need a new model, you need a new calibration zone as well. So the less changes we have, the better. But then there's our model. So I see a very simple sort of generic CO model might look something like this. Porosity versus CO. This is a limestone model, so it's going to be this shape, because even if there was no hydrocarbon involved, as your porosity increases in a limestone or a carbonate, your amount of carbon is decreasing. So just porosity alone can have an effect on the CO ratio. And then obviously if you have different oil saturations in there, that's going to increase your CO ratio as well. Whereas if you look at a generic sandstone model, the change in porosity doesn't affect the amount of carbon in the system. So it's more of a flat line, but it would just change dependent on the amount of hydrocarbon. So where'd you get your model? So if you're working for an operator and the service company is log, they should be able to provide you with a model. Some of the service companies have given us models we've already got in here. But if it's not here, you can, and you get maybe even like an image of the model from a service company. You can go to user models and you can just start building your own model by typing in the parameters here, and you could save that to your database. Or you could use a generic one. Now, if you're using a generic one, it's even more important to have good calibration zones in your data. So those wet zones and clay zones are even more important if you're trying to interpret this without a actual service, a model provided by the service company. So a choice there: build your own one, bring one in from a service company, or use a generic one. This is roughly the environment that we're logging in here, so I can apply that to that zone. So that's created a zone here. It's a CO sandstone zone with a linear model. So now I've got enough information. I've got the data coming in, the borehole information, the response model information, my parameter grid set up, so I can just run this, make my plot. Again, here's our synthetic. So this is open hole data, cased hole data. So we can compare. These zones were all oil bearing initially. Now you can see most of them now appear to be water swept, except perhaps the top one, which looks like there's still a hydrocarbon in there. Now we've got two tracks here. One is clay corrected, the other one is unclay corrected. They both are identical because I haven't put a clay correction in yet. I'm about to do that. There's two things we might want to do. We might want to normalize the model to the data. Even when you get a model created for this exact environment from the service company, don't always end up, the data doesn't always end up sitting nicely in the model. So you can, in the software here, take the model and try and fit it better to the data. See, I'm moving that up and down. As I do that, you can see the interpretation updating live to show how that would affect my interpretation. So again, I'm expecting these the data to sit within the envelope here. You can see some of the values coming beyond the 100% water line. So perhaps this model should be, moved down a little bit. That probably gives a more realistic residual oil in those lower zones as well. The other thing that we haven't corrected for is the clay. So I can open another cross plot. This time clay versus CO. And again, I don't have a good clay volume. Now see how the CO data stopped here. Now, if I was involved in the planning of the job, I would have said, please just continue logging into that clay. And I would have had a nice line here on my cross plot. Fortunately, I don't have that. I've just got sort of 50% clay is about it's almost as good as I've got. Maybe a couple of bits up at 70, but so it's quite harder to get an accurate trend, but it's probably going to be something like this. It could be, maybe that's the trend there. But as I've done that, you can see the clay corrected model has changed. And it's starting to make more sense now. In the previous one, it looked like we had a lot more oil in this zone, but that was also a zone where we have a lot of increase in clay. When we put in the clay correction, you can see that it's changing a bit. If I put in something even higher, so you can see it's actually looking more like the model's looking more like the data now. And it's showing that bump in CO is actually down to clay, not down to more oil. So that's kind of corrected that situation there. So the reality is probably something in between here. So once you've done your clay, you might actually end up having to readjust your wet line as well. So those are the two main things, clay and wet zone normalization. You can adjust those bit trial and error and see how it affects your result. You'll know when something doesn't look particularly right because it will start, the data will start stepping out of the model. But there's our kind of reasonable result that we're looking at 2 wet zones and 1 zone that's looks like still hydrocarbon bearing. Looks a bit wetter here. This probably needs to be down a bit again, but there will be a lot of noise with CO as well. With CO, I don't think you can really look at the saturations and say, okay, so we have 46% water saturation at this depth. It's not that accurate. I think with CO, you're really looking at these results and saying, okay, this zone now looks wet compared to what it was. This zone now looks similar to what it was. Or it might be something in between. You're not really going to get exact, down to the exact saturation, but it can give you a very good indication of whether there's hydrocarbons behind casing or not. So that was just the CO module that we saw there. But what about gas? So Sigma can handle gas or oil versus water in high water salinity. If you have low water salinity and you've got oil, you probably want to use CO. CO is not particularly good in gas. So there's a gap there if you've got low or unknown salinity, but you've got gas in the gas presence, then there was a bit of a gap there. So a lot of service companies didn't developed. Now, I've just called this a kind of gas-liquid mode. For example, Baker called this gas view, and Halliburton, I think it's SAT SG or gas SG. I can't, but so they've all got a kind of their own name for it, but they're kind of doing something quite similar. Now, what we're looking at this time is that source burst, same area as we looked at CO, but we're not looking at the energy, we're looking at counts. And we're looking at counts between the short space and the extra long space. The reason we're doing that is because if you have gas in the environment, the neutrons will travel much freer through gas. Gas isn't as good at absorbing the neutrons. So what you'll find is you'll get counts on all three detectors if you've got gas in the formation. Whereas if you have water in the formation, you may only see counts in the short space, long space, but hardly any, if any at all, on the extra long space. So this extra long space detector is just in that sort of sweet spot that you will see gas, you'll see neutrons, sorry, I'm saying neutrons, it's gamma rays we're seeing again. Gamma rays from a gas environment, gas reservoir, but you won't see from water reservoir. So looking at the ratio between short space and extra long space gives us our ratio of inelastic curves. The workflow is very similar to what we just looked at with carbon auction, but this time we're looking at models that are actually, looking between gas and liquid, because these curves will respond very similar for oil and water, which is a good thing, because that way we can isolate the gas response. But same idea, bringing model together with data, doing some calibration, and ultimately getting a gas saturation curve this time. Let's say, so that this is actually done in the carbon auction module, but just using a different data going in, different data coming out. But and the reason we did it in the same module as carbon auction is because we thought people might want to zone the analysis. So here's an example of, you might be logging two completely different reservoir units. So the lower reservoir units are looking at oil and water, but then there's a completely different reservoir above that might be gas and water. So you could log two different logging modes and do two zoned interpretation in the same module, in the same run, but one zone will be doing a gas analysis, one will be an oil water analysis. So that would be if you've got gas and oil reservoir, but not in the same place. If you had maybe three phases, you could potentially do two separate analysis, one using carbon auction data, one using gas analysis data. So for example, in this zone, we've got gas in the bottom here. The CO looks a bit confused because it says water, oil, water, oil. It seems to think there's water on top of the oil, which would be a bit strange. But then when we look at the gas analysis, we can see that there's a high gas saturation there. So if you bring the two together, you can start getting a picture of perhaps as like water, oil-water contact here, than a gas-oil contact here. So that's, rather than a zoned analysis, you're doing two analysis over the same zone and then bringing them together to make a three-phase. So I think I'm just looking at my time. So yeah, I went a little bit over the hour there. So I will stop there. And yeah, so that was, as I say, to summarize, there's a lot of different tool types on the market. Those different tool types will have different logging modes for different environments. They will have different names for doing those types of services, but some of the services are quite similar between the two. So, you can apply quite generic workflows for interpreting data from all those different tools.
Okay, Ross. I believe you conclude your presentation.
Yes.
This is very
Yes.
Oh, okay. So thanks for your effort and for this really informative presentation. Like having also, you highlight the strength of software to deal with the carbon oxygen. It's really good. So I believe there is a few questions on the chat box if you want to take a look.
Oh, yes. Okay. While processing the data, is there a probability factor used in the correction fact? We could actually put this through a Monte Carlo simulation. So you could actually put, I mean, there's going to be a certain amount of error in, if you're talking about carbon oxygen, for example, there could be like a sort of 15% error in the measurement itself, depending on how many passes you do. And your calibration, there could be a bit of error in that as well. So we could do an error. It's not done within that same module, but the results can be used in a Monte Carlo error analysis, which would give you a probability if you put in a range of different parameters, if that's what was meant by that. Sorry. If open hole prostate is not available, how would you calibrate the sigma log? If there was no prostate, I mean, we could calculate a lot of the ratio curves that are logged alongside the sigma curve are responding to porosity. So we could potentially try and calculate a porosity from the pulse neutron data and then do the saturation analysis based on that porosity. I would always much prefer to have an independent porosity coming into the model. But there are ways that you could calculate a porosity. And we'll probably be hearing about some of the sort of spectral analysis that are done on some of the newer tools that I believe that they're from that they could calculate a porosity alongside the saturation. So that's maybe something that some of the service companies will talk about in the upcoming sessions. As file test, what's the effect on SWCO? Well, any change in the environment is going to have an effect on the model. So it would really have to be modeled. So anything special about your environment, whether that's fluids or lithology, you'd really need to get that modeled by so each of the service companies have the ability to model for their particular tool. If you give them the exact fluid and lithology parameters and porosity, they should be able to show how their particular tool would respond to that. A pi neutron logged by a sigma log to naturally fractured reservoir. Can I also accurately identify secondary porosity? Potentially. So a bit like so we saw that material balance equation where we're trying to solve for saturation. To do that, we need to know what your porosity is, what your clay volume is as well. But of course, though, that material balance equation can be rearranged, and you could solve for porosity. However, you then need to make assumptions about the other things in your environment. So if you are confident in your saturation at that depth where you've got fracture, perhaps, and you assume it's 100% water or whatever, you could perhaps infer the porosity at that fracture. So yeah, we can. All these things are possible if you have a good hand on everything else. we can accurately solve one thing at a time.
Yes, I will not really depend on sigma for fracture. Maybe image tool will be much better, like let's say tool for this one.
Yeah. Flowing. That's a good question. Sigma analysis can, be logged, or sigma logs, shut-in and flowing. Carbon oxygen could as well, but I think the best scenario for pulse neutron logging is an unperforated zone that's the well shut in, and there's one fluid in the borehole, and that allows you to see. So everything else is consistent, so you're able to see what's happening in the reservoir. Once you get to perforated intervals and there's flow and there's fluids are changing in the borehole and there's invasion, things become a lot more complicated. The good thing about sigma is it can see quite deep into the formation, so it could see maybe beyond the invasion. Carbon oxygen, not so good depth of investigation. So over a perforated interval, you're probably likely just to see the invaded fluids. So yes, flowing passes can be maybe interesting if you're doing a sigma analysis. Maybe you want to see if there's a difference between flowing and shut-in, maybe to get an idea of how much invasion you're seeing. Carbon oxygen, I don't really think works very well over perforated zones or flowing. Are you guys in the US as well? Yeah, if you're referring to Geoactive, yes, our headquarters are in Aberdeen in the UK, but we have an office in Houston as well. I think that's it for questions.
Yes. Thank you, Rose. Thank you so much for this lecture. Okay, Kate is saying she's in Houston, Texas as well.
Just giving her a
Great.
thumbs up.
Yes. So I believe the contact information for US office on your page, on web page.
Yes, or yeah, anyone here can contact myself directly as well.
Okay. This is amazing.
There's another question just came in there. Can we use Sigma CO for water shutoff?
Shamam.
Yes, it's very useful for doing water shutoff. Well, if you're a lot of the time we're trying to make decisions on water shutoff and where we might want to perforate as well. So a mature well, it's producing too much water. We could go with a CO log and a production log, maybe see where the water's coming from. Is it possible to shut that water off and use the pulse neutron tool to see, is there any other zones that we could perforate while we're there as well to increase production? So yes. But yeah, any other questions? If anyone can contact me directly, it doesn't really matter which location you're in. We can contact you and arrange a meeting.
We have received something. We'll forward to yourself as well by our side.
Yep.
Okay. So I would like to thank you again for this informative and fruitful lecture. And thanks for your efforts, and thanks for Geoactive usual sponsoring. As you mentioned, along with this series this year, we have a confirmed event with Baker Hughes. They will talk a lot about their RPM tool. So some of these questions that highlighted now, they can maybe go more deeply with the tool manufacturer itself. We also have one lecture with Schlumberger, but they will talk about their pulsar for open hole application, okay, and one with Weatherford as well, okay. But for sure, RPM Baker will be a lot about the case hole, okay, itself. It will be mostly have been confirmed to be in May, okay. We'll announce about the exact dates later, okay. Dr. Mohammed, any last word?
Yes, Mr. Mazen. Dear Mr. Rose Brackenridge, on behalf of SPWLA Iraq chapter, we extend our sincere appreciation for your insightful and highly informative presentation. Dear attendees, thank you for your participation in today's webinar. We truly value and continue your continued interest and engagement. We would like also to extend our sincere thanks to Geoactive Limited and to all our sponsors for their support, which made SPWLA Iraq events possible. We wish you success and look forward to welcoming you to our future events. Thank you and goodbye.
Thank you, Dr. Mohammed. Thank you, Mr. Rose, and thanks for all our attendees. Have a great day. I will conclude the meeting. Bye-bye.
Thank you. Bye now.
Bye-bye.